My name is Catherine Deverin, and this is Lab 2. The purpose of this lab was to extend our work from Lab 1 and determine a more precise estimate of the amount of charge on each piece of tape, so that one can float over the other. Instead of modeling the tape as a point charge like in Lab 1, we modeled it with the charge evenly distributed over its length. As shown through these two diagrams, in Lab 1, we used the tape as a single point charge and calculated Q based on the electric force and the gravitational force. But in this lab, the tape will be modeled as a distributed charge. The fundamental principles used in this lab are Coulomb's law, which we use to calculate the electric field and is shown through the diagram on the slide, as well as Newton's second and third laws. Another fundamental principle is superposition for distributed charges. By dividing the tape into several segments, each segment could be treated as a point charge, where we would then find the electric field for each of these segments. By summing the electric fields for each of these segments, or point charges, we could get the net electric field. The main results I found was that with n equals 10 segments, the charge of the tape was calculated to be 2.6376 times 10 to the negative 8 coulombs. This value was estimated using a computational model so that the system will reach equilibrium, where the gravitational force equals the electric force. Because this lab was essentially an extension of Lab 1, I used the measurements that I found from the first lab, such as the length of each tape, the mass of each tape, the distance where the tape begins to float, and the electric force and gravitational force. New assumptions put in place were that the charge is evenly distributed across the tape and that we can divide the tape up into several segments and treat them as multiple point charges. This way we can superimpose each point's charge's electric field, ignoring within each tape. The goal of the code in this lab was to computationally model the tape with the charge evenly distributed across the length of the tape. This means we need to model the gravitational force on the top tape as well as the electric force of the bottom tape's point charges on the point charges of the top tape. As shown on this slide, I used the values from Lab 1 and the function for electric field to start. The next part of the code created a line of point charges distributed evenly along the length of the tape. This would allow us to model the tapes as a collection of point charges in a line, as shown through the code for the top tape and the bottom tape. Next, we had to model the electric field and forces through arrow vectors. There's an electric field at each point charge, dq, in the top tape from the charges in the bottom tape. Therefore, we need to create n arrows for these E-field vectors. This is represented through the code that is highlighted in blue on the screen. Like in Lab 1, we also needed to model the net electric and gravitational force of the top tape. These are shown through the vectors FE arrow and FG arrow, where the axis for the electric field is the electric field of the top tape, and the gravitational force vector is represented through the y component of mass times gravity. This image represents the computational model from the code. The red spheres are the point charges of the top tape, and the blue spheres are the point charges of the bottom tape. The white arrow in the positive y direction is the net electric force of the bottom tape point charges acting on the point charges of the top tape. The yellow arrow in the negative y direction is the gravitational force on the top tape. Finally, the green arrows are the electric field for each point charge dq in the top tape. The magnitude of the electric force and gravitational force are equal with our new calculated value of q. In conclusion, if we had modeled each of our tapes as a single point charge like in the previous lab, the q value that we calculated was 2.07 times 10 to the negative 8 coulombs. In this lab, on the other hand, with the line charge model representing the tape, I calculate Q to be 2.67 times 10 to the negative 8 coulombs. These estimates differ, because the Q from the tape with the charges evenly distributed is more likely to be closer to the real value. This is because a 0.13 meter long tape cannot be accurately represented by a single point charge. The most accurate answer is when the tape is divided into an infinite number of point charges, so Lab 2's method of dividing the tape into multiple point charges will be more accurate than a single point charge. The most accurate answer will come from dividing it up into an infinite n amount of point charges.